All right, so we are just going to finish up then going over some of those functional group absorptions for IR. And then, then we're going to do the problems. They're only going to have NMR, but the problem set here has IR mixed into it as well.
This will be just NMR and IR in the first exam.
And UV Viz.
And UV Viz.
Yeah. Yeah, so print out that copy that's on the website under the UV Viz, right with the notes there.
What is a big one? I think that's a big verse.
It's like a chapter in the book. Okay. So we talked about CH bonds, we talked about alcohols, amines, things like that. So the next thing is to talk about carbonyl compounds. All right, and so carbonyls, they all have this carbon-oxygen double bond, gives a prominent stretch, strong and reasonably sharp, but it can vary a little bit over some range of values. So if we kind of think about a ketone, let's just think about that as a generic carbonyl group. And this has an absorption in about 15 reciprocal centimeters. So let's say that's cyclohexanone right there. So the other carbonyls, it depends on what's attached. So if we put some kind of other group here, this other group can do one of two things. It can either be an electron withdrawing group that's pulling electron density away from the carbonyl and away from the delta plus that's, developed on that carbonyl carbon. And when that happens, the electron density on the oxygen kind of gets pulled down, and what this does is it actually strengthens the CO bond. Okay? And if it does that, then the absorption is going to go to a higher wave numbers, or higher, let's just say higher reciprocal centimeters. Okay?
Around what wave numbers will go around?
Yeah, we'll look at some values here. The other thing that this Y group could do, if it has non-bonding electrons on it, it can have resonance with the carbonyl. So if it donates electrons this way, then these electrons go up onto the oxygen, and so we have resonance. It's like this, and so this is adding some single bond character to the carbonyl. All right? And so this is going to weaken the carbonyl group. So this would shift to a lower frequency or wave numbers. Okay? And so different groups can do different things, and some of these oxygen and nitrogen things here do both of those. They're more electronegative. They're going to pull electron density, but they also have non-bonding electrons, and so they can donate it. So it's this balance between inductive effect and resonance. Okay? We already talked about if we have systems that have conjugation like this, these end up being more electron donating groups like this. And so this shifts up to about 1674 reciprocal centimeters. Okay. If we have an ester, of course, the ester has non-bonding electrons here, but oxygen does a little bit more electron withdrawing than it does donating, because oxygen is more electronegative. It's not as good at holding a plus charge. Okay, so this is actually, let's see, 1750 to about 1735. All right, so it goes a little bit above the ketone. If we have, this will fit in here, an amide, right? It's also more electronegative than oxygen, but nitrogen is more electropositive, so it's better at donating electrons. And so that's the kind of the mode here that dominates. And so this has this resonance like this. Okay, and so amides are more in the 1695 to 1650.
So in esters, the oxygen strengthened the bond between the carbonyl compound,
Right.
carbonyl group, and okay.
Yeah, because it's pulling electron density away. I guess it's kind of increasing the delta plus, but then the oxygen compensates by donating some of its electron density into that bond. At least that's kind of the hand-waving argument here. Okay, so we have a little bit of range. Sometimes it's a little bit hard to pick out in the spectra, but let's take a look at some of these other ones. So here is, I think this is one. So this is supposed to be at least around 1715. All right, and in this, we just see the regular other stuff, the CH stretches, and, I guess in a ring there's more like other modes, so we see a more complicated fingerprint region. Okay, so there's cyclohexanone again, and we're going to add other functional groups in. So here's cyclohexenone. It's hard to tell here whether it's actually shifted to a lower wave number, but what we do see is we see this peak here above 3,000. So this shows the stretch to the sp2 hybridized carbons, right? And the rest of these are to the sp3. And it's pretty weak. There's, probably somewhere down in there is some carbon-carbon double bond stretch as well. But maybe it doesn't just go itself. It's all kind of some bigger modes with the carbonyl as well. Okay, aldehyde. So this is benzaldehyde. Have another unique stretch. In addition to the carbonyl stretch, and they're pretty similar to ketones, but they have this hydrogen that's attached to the carbonyl, and that gives kind of a unique pair of peaks right here. So these are for the aldehyde, and I think it's kind of combined with the carbonyl. It ends up being kind of a symmetrical and asymmetrical stretches. And notice that these are a little bit to a lower wave numbers than we see for alkenes. So it's a little bit different. They're attached to sp2 hybridized bonds, but they're a little bit on the other side. So usually we see two peaks between 2830 and about 2695. So benzaldehyde doesn't have any sp3 hybridized carbons, and so, but usually if it did, those would be like right in here, and this pair of peaks would be on the lower edge, okay, for an aldehyde. So the combination, a lot of times with these carbonyls, what we look for is the carbonyl, And then we look for if there's other peaks that are associated with it, right? So the ketone is essentially just the carbonyl, right? But if we have an aldehyde, we have carbonyl plus this pair of peaks. If we have an ester, we've got the carbonyl peak here. We have, both, I won't label these, but we have both carbon-hydrogen stretches for sp3 and sp2. And we have some, it's really complicated, but we have some strong peaks down in here, which no, that's not what it was. I would hypothesize would be carbon-oxygen stretches. So maybe even there and here, because if we have something like an ester, ethyl benzoate, it actually has 2 carbon-oxygen stretches. All right, and we see here's probably some overtones that are at least consistent with the presence of a benzene ring. All right, and if I can pick that out, let's see, these are 19, 18, 17, so that is definitely up over 17. What is it supposed to be? 1735, I don't know. So yeah, there's the line for 17, and so it's a little bit higher than that. Okay, if we have a carboxylic acid, these have kind of a characteristic shape as well. Right, it has this OH, but the OH ends up being really broad and it stretches all the way, past all of this CH stretch region. And I think partly it's because, they can have these intramolecular hydrogen bonds as well.
Is it intramolecular or intramolecular?
Oh, intermolecular. Yeah. And they could do it in a ring like this, which is pretty stable, or they could do, out like this, but there's a bunch of, kind of OH stretching modes. And then we have the carbonyl stretch here, and we probably have, one of these down in here is probably some carbon-oxygen stretch. I'm not sure which one. Let's see, what's that? 19, 18, 17. Seems like all these carbonyls are like 1,700. Okay, so the next one is an amide. And we see these are the NHs of the amide. And they're much more pronounced than the NHs for an amine. But notice here again, if we have 2 NHs, we get 2 peaks. And if it was a secondary amide, if there was only 1 NH, we'd have only 1 peak there. Okay? And then this carbonyl is really broad as well. And let's see.
Why? Because the carbonyl can be broad, or because of the nitrogen?
It may be because of the resonance as well, because we kind of have, the resonance, you don't have like a mixture of carbonyl stretches. You have one resonance, but maybe when you put in the...
so the resonance between the carbonyl and the nitrogen?
Right, but I don't think that would necessarily broaden that, because, resonance isn't an equilibration between different structures, right? It's just a hybrid of the different structures.
And it's more in this state, I think, rather than being resonance with the nitrogen. Because of the more electronegativity of the oxygen, probably.
Well, this one is with the nitrogen, right? So remember, the nitrogen is better at donating. But maybe there's some hydrogen bonding with that carbonyl here that ends up broadening that too. But notice this one is, I think, at 19, 18, 17. This is at like 1650 or something like that.
Lower.
Yeah. Oops. Okay. So, I think, we can always look at these tables and stuff like that, but I think that we can do a lot by just knowing a few regions, right? So, down here, down here we have NH and OH, then we'd have some region that has the CH stretches on SP, then we have the CH stretches for SP2, and then we have the CH stretches on SP3, and then right in here we have aldehydes, the CH stretches for the aldehydes, which give 2 peaks in there. And then somewhere in here, in this middle region, there's going to be triple bonds. Right, and these are going to show up more if they're unsymmetrical. Right, you could have a internal alkyne, but it has different groups on each end that does show up here. If it's perfectly symmetrical, you won't see it at all. Nitriles are in this region as well. And then we have the carbonyls. We have in here the C double bond stretches. And then we might be able to pick out down in 1200 to 1000 the CO stretches, but those are oftentimes kind of buried in the mix. But if we see kind of a broader than normal one down there, then we might be able to use that. All right, so beyond this, if you look in the book or if you look at details, they talk about things, if you have an isopropyl group versus this alkyl group, so, there might be things like that you could dig out of it if you really want to, but we're going to get most of that kind of thing from the NMR.
And when we have OH, usually it covers all the peaks in that area.
Oh, well right, so if it goes all the way like this, then that's kind of the carboxylic acid. And those are like super broad, not just like an aldehyde, alcohol that's kind of a symmetrical kind of thing that doesn't run into the CH region. All right, so here's just a couple of easy ones for just IR. So what do you pick out? So we got CHs, we got a carbonyl,
but we have a broad peak at 12.
And we got a broad peak at 1200, which, could be a carbon oxygen, right? So that's why we know it's not the carboxylic acid. It's not the aldehyde. There's no CH stretches for the aldehyde. So the question is between the ester and the ketone, and so it boils down to whether we have a CO stretch or 2 down in there. So I would agree, probably B. All right, here's one more.
We've got the broad peak on the left.
OH, CH.
There's no carbonyl peak, right?
There's no carbonyl peak.
All the CH bonds are less than 3,000.
All the CH are less than 3,000, so there's no double bond. There's no double bond, right? So it's just and maybe in here, though there's other peaks on top, there might be a carbon oxygen or something like that. All right? So that's all I got for IR. All right, so I think all we're going to do then, we've got quite a bit of time, but just go to this other website and work some problems. I got stuck in front of my computer going through them last night. I couldn't pull myself away. All right.